Hi everybody, welcome back to part 3. In the previous part, we talked about how Bob and Jan were able to agree on a secret key, in our example, the color purple, without ever meeting each other and without letting Kim, who's eavesdropping, know. It was really cool. It was like magic. Now, that brings up a very important topic in computer science and encryption called one-way function. Function. And in our painting example, it was easy to mix those colors, but once we got that color purple, it's really hard to reverse it and figure out what colors made that up, right? So it's easy in one direction, but to reverse it, it's very hard. So to figure out what colors made up that purple, it's really, really hard. And this is called a one-way function. Now we're going to introduce numbers, and we're going to get closer to the Diffie-Hellman method. We're almost there, I promise. First, I'll introduce something like, well, forget that. I'll do an easier example. 46, sorry about that again. 46 mod 12. There you go. So 46 mod 12 modulus will give us 10, and and this is called congruent. So 46 mod 12 is congruent to 10. And you can think about this like a clock, and you have 12 points, and if we had a rope that went around like this, eventually it would end at the 10 mark. So we have 10. The other way you can think about it is 12 times 3 is 36. We can't go one more, so it'll be remainder 10. Okay, cool. So if we had something like 3 to the x mod 17, we could have, and this x can be any number, we'll have any number between 0 and 16, and any of them will be equally as likely. Right? We'll have any number between 0 and 16, and any of these numbers will be equally likely. To go from here, if we had something like this, we know what it's congruent to, but we want to figure out what the exponent is. This is called the discrete logarithmic problem. Problem. And this is very hard, and now we've introduced with numbers a one-way function. Because to go, if we had 3, this should be 29 mod 17, we can easily say what this is congruent to. This is easy. But if we wanted to go the other way around, this is very hard to reverse it. And basically you'd solve it by trial and error. Now, you might say to yourself, okay, a computer can solve this by trial and error pretty quickly because computers are so fast. But what if we had something like a very, 100-digit number, and we asked the computer to solve this? Even modern day computers would take thousands of years to solve this. And before I run out of time, this reveals a very important aspect of one-way functions, in that the strength of a one-way function is how much time it takes to reverse it. I'll see you in the next video.